Um, we can then move on to our fourth speaker, Professor J.D. Anand, who is one of my former teachers at Delhi University and a former colleague of Professor A.N. Mitra. I'm very happy to welcome you to give your talk here. Please share your screen.
Thank you, Professor Jain. Hello.
Yes, we can hear you and see your screen.
Yes. Okay. Is it okay?
Yes, please. Yes, you can start. We are able to see things and
I'm grateful to the organizers for inviting me to this talk, and I had a long association with Professor Mitra since 1960, when he joined the department as reader. I was then pursuing my PhD thesis under Professor Majumdar, and Professor Mitra took a lot of interest in students of Professor Majumdar also. So in the early 60s, there was a lot of interest in Reggie poles, dispersion relations, resonances, and particle physics. So at that time, Professor Mitra was pursuing the separable potentials. So he suggested that why don't we apply separable potentials in the complex angular momentum plane. And that originated of our writing a paper on separable potential in the complex L plane, which we published in Physical Review 63. After that, I had another paper with Professor Mitra on PP scattering and Regia's interaction, which we published in 65. So these two papers became the part of my PhD thesis in 65. So Professor Mitra took a lot of interest in my development. He recommended me as a UNESCO fellow to visit USSR in 65 and 66. And he also recommended, when he was the head of the department in 74, he promoted me from permanent research associate to permanent lecturer in 74. So I had a lot of personal contact with Professor Mitra. He attended my marriage also in 1966. So he was he helped me in promoting multiple theoretical physics areas. So I owe him everything which I have developed. So actually, I have to choose a topic because now I am 25 years behind this research, and I have chosen a topic which we had collaborated with my colleagues on various aspects of neutron stars. We had actually uh, studied mass radius relation of neutron star and bulk viscosity and uh, emission of neutrinos and antineutrinos as the process of cooling neutron stars. So I had a collaboration with Professor Ashok Goel, V.K. Gupta, and Santokh Singh. So we had a number of students also. So a lot of people may be knowing now what are neutron stars. So neutron stars are formed because neutron stars are formed from the remnant core of the massive collapsed supergiant star. And this neutron stars is the densiest object in the universe, second only to black holes. And typical properties of these are mass is about 1.4 or so, radius is about 10 kilometers. And it is composed of mostly neutrons. So protons and electrons, they fuse under pressure to again have additional neutrons. So since and at this temperature, neutron has a high temperature also, and this at the same of at the time of formation, it when it is collapsing, what happens is that the rotation, its rotation is increasing due to the conservation of angular momentum. So this neutron star is actually supposed to be stable due to the neutron degeneracy pressure, like the degeneracy pressure of electrons in the white stars. So, so in the case of neutron stars, previously, Jana, it was found that the neutrinos and antineutrinos as produced from the neutrons are not sufficient. But with the latest detection of neutrinos and antineutrinos, this reaction n going to p plus e plus neutrino, antineutrino, and n plus p plus e is going to n plus new electron. So these processes become important. And if the energy of the electron is very high, then muon couple paper pairs also take part. So I have just given a one positive known PSR. So this is about the neutron stars, because a lot of people know now neutron star very well. So I will actually, I have chosen a topic of radial pulsations of neutron star, and this was published by me and along with my friends. So I would like to report this thing in this colloquium. So in studying the radial oscillations of neutron star, it is important to have a equation of state is equation of state is very central to this, because if we know the equation of state well, we can do a lot of things. Now, it is very, we don't have an equation of state for all the energies. So there are actually a lot of cases for the high energy as well as low energy equation of states. So the famous equation of state, and at the same time, we also know that in the case of neutron star, there is a strong magnetic field at the surface as well as interior. So at the surface, the magnetic fields are of the order of 10 to the power 13. And interior also, the magnetic fields are quite high. And these neutron stars are known as magnetrons. So we also wanted to study radial oscillations in the presence of strong magnetic field. So for equation of state, we have chosen the low energy in equation of state from Baum, Patrick, and Sanderson model. And in this model, the pressure of the hadron matter below the neutron drip is given by this thing. And this electron pressure is also given. The lepton pressure as well as energy is given. The number of electron is given. And along with the right-hand side, I have given a table where for the medical purposes, the table is useful. So the matter consists of, if I consider an atom having A and Z, and we can write down the energy, and at the same time, we can find out uh, the energy as well as pressure from this thing. So for high energy, we have chosen the relativistic mean field theory as given by the ellipse, given by ellipse. And we have incorporated the magnetic field modification due to the particle momenta and density. Actually, the pressure is given like this thing. The first part is the pressure due to N, P, and E. And we have also taken omega as well as rho mesons. We have also taken the scalar sigma particle. So we have written down the pressure and energy, and the potential of the sigma is given. So, so these neutron, proton, pressure and energies we have given in details on the right-hand side. So when we want to find the pressure and energy, and they depend upon the magnetic field, they depend upon the. So what we have done is that we can choose a nuclear density, and from that thing we can find the parameters of the pressure and this thing, and then evaluate the pressure and energy, which we will be using in the Tolman open number equations. So here the chemical potential, because we have actually taken the neutron as a degenerate free particle, and the chemical potential of the neutron is given by proton and electron. So for radial oscillations, we have taken a small perturbations, and they are governed by the general relativistic equations, which actually Professor Kulshist has talked about. So the Tolman open number Volkov equation is written on the right-hand side, and it involves the pressure gradient, mass gradient, and nu. We have chosen the ds square as this thing. So the here delta r by r are new variables which we have chosen. So for given density, because for given energy density, pressure and energy are obtained from the equation of states and used to calculate mass and radius from these equations. And because we have chosen the time dependence of the harmonic oscillation as e raised by I sigma t, and we have written down the equations governing radial adiabatic oscillations as 41. And this is the famous Stern-Liouville eigenvalue problem. And from the properties of this equation, we can see, and the variables f, g, and h are given on the right-hand side, along with lambda and adiabatic index. So the boundary conditions to solve the equations are that zeta at r equals 0 is 0, and the pressure change in pressure at capital R is 0. With these boundary conditions, we solve these equations, and it is an eigenvalue problem, and it is from the properties of this famous eigenvalue equation, it is clear that sigma square is real, and the fundamental mode is greater than other things. So sigma 0 is greater than sigma 1, sigma 2, and so on. So by combining equation of state both at low and high energies, I have just, we can find out the model of the neutron star. And here the magnetic field we have chosen as 0, 1 in 10 power 3, 5 in 10 power 3, 1 in 10 power 5, MeV square, where 1 MeV square is 1.69 into 10 power 14 G. And the various coupling constants are given on the right-hand side, which we have chosen from Alice. So we solve the Tolman-Wolff equations for mass radius relation, gravitational shift, and density profile elevated gamma. So by solving these equations, we find the fundamental and excited these frequencies. So the results are that mass radius relationship with magnetized neutron stars support higher masses and strong fields, more compact configurations. So we have plotted for A, B, C, D on the right-hand side. So mass redshift relationship is also plotted, and redshift increases with mass and magnetic energy. Can be an observable indicator of field strength. And for in the third figure, we have given the this thing pulsation periods, stability and pulsation periods we have given for typical neutron star of 1.4 mass, solar mass. And magnetic field has the minimum effect on radial stability, and pulsation frequencies are not significantly altered in this mass range. We have done this thing for first excited mode also. So we conclude that magnetic fields affect minimum mass and compactness, but not affect the stability of the typical neutron star. Helps define models for magnetrons and related astrophysical events. Sets groundwork for future studies involving gravitational wave emission and magnetic fields. And we have also incorporated the temperature effect in the other papers. So I will give the references for our completeness. And thanks, Sanjay Jain. Thanks, Professor.
Thank you, Professor Anand, for the talk. The session is open for questions. I can see a thumbs up sign from Professor Utah in the participants list. However, yes, Professor Utah, your hand is raised. Please.
Yes. Thank
Please.
you very much for this nice talk. My question concerning your main result, that the magnetic field strength does not affect so much the stability. Do you think this is a rather general result, independent more or less of the different types of equations of state that one can use?
There you go. So, Jan, can you elaborate the question, because I'm very happy.
Yes, I think the question is one about the generality of the result. Maybe Professor Utah, you can repeat the question. I think.
Yes, sorry if I wasn't clear. You have this nice result that the modes are basically not affected by the strength of the magnetic field. And my question is this more or less independent of the equations of state that are being used? What is your opinion on that?
Actually, because I retired in 2000, and before 25 years before, and this work is done in 1998 and so on. So
Mhm.
at that time, it was quite interesting, and it was found that these nuclear mean energy, nuclear, this equation states were quite helpful at that time to understand, because I had also worked in the strange quark stars, where we had taken UDS quarks, and there also we found the mass radius is compatible up to 10 kilometers and 1 solar mass. So that is why we have chosen these nuclear equations as models.
Mhm. Yeah, I mean, these are quite
Yes, I
attractive
think it would be
equations
interesting
of mo.
to address that that question and see to what extent this independence holds, right? Um, okay, thank you, Professor Jaydev Anand. I don't see any further questions. So thank you very much for your talk.